Lesson 4.5, inverse functions. So we'll find the inverse of a function if the inverse does in fact exist. Okay, so several things here. Inverse notation. This is not f raised to the -1 power, but when you see there, that represents an inverse. So y is equal to f of x is our function. Y is equal to the inverse of f of x. That's how this is read. Two functions are inverses of each other if f of g of x equals x and g of f of x equals x. So this is what we would call our analytical proof. Okay, so that's the math that would prove it. If a function contains the point a comma b, then the inverse function contains the point b comma a. And we've seen a lot of this, okay? When we looked at symmetry over the line y is equal to x, okay? We said if the point x comma y was on the graph of the function, then the point y comma x was also on the graph of the function. So we'll look at this again because inverses are reflections about the line y is equal to x. So the fact that these values change should not be brand new to this chapter. All right, inverses algebraically. So just let's recall the composition of functions. So we work from the inside out. So g of 2 would equal 24. And then when I plug 24 back into f, I get 2. F of 36 would give me 36 divided by 12 would give me 3. And then g of 3, 12 times 3 would equal 36. So notice the final answer to those compositions relative to the original. X started as my input and it was my final output. In number 2, 36 started as my input and it ended as my final output. Okay, so think about what it was just defined, what the inverse was just defined as. G of f of x has to equal x, and at the same time, f of g of x has to equal x. So now, in numbers 3 and 4, we'll actually prove that. So I take g, the function g, and I plug it into the function f. So f is 1/12 times g times x, and I'm replacing x with 12x. 12's cancel, leaving me with x. So both conditions have to be true, right? So if we did f of g, now you have to prove g of f. So the function g is 12 times x, and I'm replacing x with 1/12 x. So that equals x as well. So it does in fact prove that those functions are inverses of each other. Okay, determine the inverse function and graph each. So to define an inverse, replace, switch, solve. All right, you did plenty of this last year. Replace f of x with y, switch the x and the y, and then solve for y from its new position. Y equals 5x plus 2. And then we literally just switch x and y. Okay, hence that note from the very beginning slide. And now to solve for the new y, I'm going to subtract 2 and divide by 5. Now to use proper function notation, that's where I would introduce that inverse. And then for number 2, replace, switch x and y. And then to solve this one, I would take the square root. But remember, when you take the square root, 2 answers exist. Okay, and we're going to talk about the domain of inverses in a minute. So -4, if I were to solve, it actually looks like this. So there would be 2 functions, -4 plus the square root of x, and negative 4 minus the square root of x. Okay, so I'll come back to this when we look at the graphs on the next couple slides. Okay, so 5x plus 2, y-intercept of 2, slope of 5, 1, 2, 3, 4, 5. I'll go down 5 and left 1. So here's my function. Okay, so I know we have an equation for the inverse, but let's use that ordered pair. If 0, 2 is on the graph of f of x, then 2, 0 better be on the graph of the inverse function of f. And likewise, using my slope, I got negative 1, negative 3 to be a point on the graph of f. So negative 3, negative 1 better be a point on the graph of the inverse function. Okay, so now 2, 0, negative 3, negative 1. And when I connect these, that would be my inverse function. Now from the previous slide, we got our inverse to be x minus 2 all divided by 5. So that's 1/5 x minus 2/5. So now my y-intercept is going to be at about negative 0.4, and my slope is 1/5. So if I look between the points that I sketched, up 1, 1, 2, 3, 4, 5, and right 5. Okay, so either one of those would be acceptable. If you know two ordered pairs on the graph of the function, you know two ordered pairs on the graph of the inverse function. And we know that because they possess the property that if xy is on the graph of f, y comma x has to be on the graph of the inverse. And then, like I said earlier, these, a function and its inverse, are reflections about the line y is equal to x. So here's our line of reflection there, and then those, again, those pieces match up. Okay, so now when I look at this, I have a quadratic. My vertex is at negative 4, 0, because it's a horizontal shift. I have my 2 points here, 1, 1. So now the deal with this, if I were to look at the points, so here's f of x. I have negative 4, 0. I have negative 5, 1. And I have negative 3, 1. So then, according to the rule, 0, negative 4 will be on f prime, 1, negative 5, and 1, negative 3. So if I graph those, 0, negative 4, 1, negative 5, 1, negative 3. Okay. So this would have been the negative 4 plus square root of x is the one function we found. This was negative 4 minus square root of x. That was the other function we found. Now I'm going to skip ahead. Only functions that are one-to-one functions will have an inverse. So what does that mean? A function, in order to have an inverse, has to pass the horizontal line test. Okay, so we've studied the vertical line test. That determines if a function, if the graph of a relation is a function. So if I look at my parabola from the previous slide, it passes the vertical line test. So this is in fact the graph of a function. When I draw a vertical line or a horizontal line through it, however, notice that a horizontal line intersects the function in two spots. So according to that, my inverse is not a function. Okay, so let me go back here. Now, why does that make sense? According to the points that I drew, now I have like this sleeping parabola. If I then go back and draw a vertical line through the function, because that's what tests for a function, notice that now a vertical line intersects the graph in two spots. So this equation here, what I graphed in green, is not a function. So what we do for that then is we restrict the domain. So if I'm looking at this quadratic, I would only look on the domain where x is greater than or equal to -4. If that's the case, then this part of the graph doesn't even exist anymore. So now if I'm only looking at where x is equal to -4, then these points would no longer exist on the graph of my function and therefore my inverse. So when I go to look at the inverse function, 0, -4, and 1, -3, now what's in red would be the graph of my inverse function. Okay, so if that's the domain, then the range would be y is greater than or equal to 0 on the graph of my function. So when I go to my inverse function, so now my inverse function would be the -4 plus the square root of x. And just like your x and your y change, my domain and range change. So now my domain of my inverse function is going to be x is bigger than or equal to 0. And my range, my y values, are going to be all my y values bigger than or equal to -4. So we'll talk about this relationship more in class, but just so you're aware, not every function has an inverse. We can make functions have inverses as long as we restrict the domain.